Systems that are cross-connected to the public water system must be connected in a manner that protects the water system from backflow. This can be accomplished in several ways and with several different devices, which include the use of air gaps, reduced pressure zone backflow preventers, double check valve assemblies, and vacuum breakers. An air gap between the public water system and any system that could cause backflow is the best method for protecting against backflow. Air gaps are acceptable in all cross-connection situations and for all degrees of risk. One major advantage of the air gap is that there are no moving parts to maintain. Air gaps provide the highest level of protection, and the gap must be 2 times the inside diameter of the inlet pipe. So here you can see a public water system discharging into a reclaimed water reservoir. So there's an air gap that is 2 times the pipe diameter. The minimum gap is 1 inch above the overflow level. So in situations where you have small diameter pipe, there must be at least 1 inch of an air gap. Another type of backflow prevention device that can be used in every cross-connection situation is the reduced pressure zone backflow preventer. It has 2 spring-loaded check valves with a pressure-regulated relief valve located between the 2 check valves. A continuous drip from the relief valve indicates that the valve is malfunctioning. During normal operation, supply pressure will exceed the downstream pressure and act to keep the relief valve shut. If a vacuum develops in the supply line, both check valves will close and the relief valve will open. This open relief valve creates an air gap between the 2 check valves and prevents backflow from occurring. Proper performance requires proper installation, which includes the assembly being accessible for inspection and testing. It should be installed such that the relief port can't be submerged because this would create a cross connection. It needs to be installed so that it's protected against freezing, and a screen should be installed upstream to prevent fouling. And it needs to be installed in a horizontal configuration or a horizontal position. In this type of valve, pressure flowing through the valve in the normal direction provides system pressure to the top of the diaphragm of the relief valve, and this keeps the relief valve closed. Should system pressure drop, such that the spring pressure of the relief valve can overcome system pressure, what happens is air is allowed in because that relief valve opens, and it creates an opening between the 2 check valves, causing the check valves to shut, and that area is vented to atmosphere, and that creates an air gap. So what you see here in green is an air gap between the public water system and the cross-connected system. Well, here we can see different configurations from normal flow to back siphonage, back pressure, or back pressure with leakage. So in the upper left-hand corner, under normal conditions, we have water flowing through this double check valve assembly, and the relief valve is closed. We have an inlet pressure of 60 psi. There's a slight drop in head or some head loss through the valve of 55 psi, and you're at 54 psi leaving the valve. So we have a pressure drop of about 6 psi through the valve. But this is normal, and these pressures will keep the relief valve closed. Well, if we have a situation where pressure drops to a negative pressure or drops sufficiently, what happens is this relief valve will open and create an air gap between the 2 check valves and cause them to close. So you can see that we have 50 psi to the right that's trying to backflow into the system that's been where the pressure's been reduced to the point of a vacuum. So where back siphonage is trying to occur, because of this air gap and the check valves closing, any leak by or any flow back towards the system would actually be discharged to the ground. Next, we have a back pressure situation where the system connected to the public system increases its system pressure for some reason. So you can see it's 75 pounds as opposed to the 60 pounds being supplied. Well, in this case, the check valve will close and not allow flow back into the system. And then the final situation is back pressure with leakage. And you can see that there's a 75-pound pressure on one side and a 60 psi pressure being supplied, and there's an obstruction in the check valve. Well, what's going to happen is, because the relief valve is open due to this difference in pressure, you'll see leakage dripping to the ground. So this is an indication that there's a problem with this check valve assembly because there's leak by. The double check valve assembly is designed like the RPZ without the pressure relief valve. This makes it so that there's no external way to tell if the check valves are leaking and allowing backflow. Double check valve assemblies are not recommended in high-risk situations in which public health could be at risk in the event of a backflow condition. And here's how the double check valve assembly works. Water flowing from left to right opens the check valve so it overcomes spring pressure, and water just flows through normally. Well, when there's a backflow condition or pressure is higher on the system that's connected to the public water system, what happens is spring pressure and the pressure of the other system overcomes the check valves and causes the check valves to close, and that prevents flow. So this acts very similarly to the RPZ. The main difference is there is no air gap between the two check valves. Vacuum breakers are designed to prevent back siphonage from occurring when a partial vacuum is formed within the distribution system. This is accomplished by allowing air to enter the line, which will break the siphon. There are two main types of vacuum breakers for two distinct applications. One type is designed for use only in systems where they will not be exposed to any form of back pressure. This type is called an atmospheric vacuum breaker. Another type, called a pressure vacuum breaker, can operate against back pressure. The atmospheric vacuum breaker is not designed to protect against back pressure, and they're only used where there is no possibility of back pressure, and they're installed 6 inches above the highest point of the downstream outlet. And the way this works is normal flow pushes this check valve up and out of the way and allows the flow to continue on through. Well, once there's a back siphonage condition, the check valve shuts, not allowing flow in the opposite direction. Pressure vacuum breakers are not designed to protect against back pressure, and they're a 2-valve assembly. One valve closes with spring pressure when the flow stops going through the valve, and the second valve opens and allows air in to break the vacuum. These valves are installed 12 inches above the highest point of the downstream outlet. And here you can see the 2-valve assembly, where normally water flows in through the bottom and out to the right. Well, when flow stops, both valves shut, and it allows air in, so atmospheric pressure in, to break the vacuum.